right, it's 11:28 and that's our cue to get started. And as we finished up the chapter or section on constitutional isomers, that moves us into the section on conformational isomers. So with constitutional isomers, the molecules were connected differently, but they had the same formula. In this case, it's the exact same molecule, but it'll have apparent different shapes because of free rotation around single bonds. So this is a little different, that we're going to look at different ways a single molecule can appear depending on the motions within the molecule. And right here I started the opening picture here with a particular view of the ethane molecule. And this is the eclipsed conformation where things are lined up, and I tried to line it up so well that you couldn't really tell it was an ethane molecule because things are lined up and the front part of the molecule is hiding the back part. So there's a front carbon here and 3 hydrogens that are even in front of that, but directly behind there is the second half of the molecule. So this eclipsed conformation is something you could recognize because things line up very well. A good idea is to read the textbook. So here's reading assignment for chapter 3 on conformational isomers. The first section will just look at Newman projections and how to represent simple alkanes. And then we'll get into conformers of cyclohexane, which will be way more interesting because we're going to look at different constitutional, conformational, and geometric isomers. So that'll take us a little while to get through. It's 6 pages in the book, and that's pretty substantial. All right, so there's a reading assignment. Make sure you pause, copy these pages down, and read those pages, maybe even before you move on. Okay, so isomers. Thing isomers have in common is things that are isomers have the same formula. And so we discussed constitutional isomers, where the atoms in the compounds with the same formula are connected differently. And we generally drew out skeletal structures and showed names for different compounds with the same formula, where the connection of the atoms were different. Conformational isomers occur when rotation about single bonds or other motion in the molecule changes the shape and the appearance of the molecule without actually changing the molecule. So no bonds are broken, nothing really substantial changes, but a lot of times the orientation and shape of a molecule is really important in how it behaves in contact with other molecules. So substrates fit into enzyme pockets if they have a particular shape, and there might have to be rotation about single bonds for those molecules to fit properly. Different conformational isomers, or conformers, which is short for conformational isomers, have different energies. When substituent groups are in a staggered configuration, there is less repulsion between groups because they're farther apart from each other, and when they are eclipsed, there is more repulsion because things are closer. When there is less repulsion between substituent groups, the molecule is more stable. And this is all energy dependent. So if you have a lot of energy, then things can go into their less stable state. There's going to be lots of rotation, lots of motion, and the molecule is going to continuously be changing shape. If you cool something down to very low temperatures, then only the most stable conformer will exist. So that's, of course, just a little introduction. We're going to look at, again, some conformational isomers, starting with one of the simplest organic molecules, ethane, which is C2H6 saturated hydrocarbon, only 2 carbons, so it's pretty easy to visualize in our mind on the paper and with the model. And so what I had built here and put on the page is the eclipsed conformation for ethane. And if you see from the front view that we can see the first carbon, the second carbon is behind there, and then there's substituents that are oriented sort of in a triangle shape facing towards us on that first carbon, Sometimes building your own model is the best way to look at this, but if I were looking from the axis of the pencil, you'd see how I'd see the first carbon, and the three things that are attached to it would be facing towards me. So in a Newman projection, the way that we draw the first carbon and the three things that are attached to the first carbon that are facing us is like this. So first carbon's in the center, and if it's ethane, you just have the three hydrogens that are pointing towards us. So there we go, molecule. Again, depending on the angle that the camera is at, it may or may not be lined up perfectly. So when it's not exactly centered, it's going to look a little offset, and that's fine. This is the eclipsed conformation. And then when I try to draw the stuff in back, if it's truly eclipsed, the stuff in the front hides the stuff in back. So to show what's in back, we just off-center it a little bit and show the three hydrogens on the back carbon. And now there's a certain distance between these electrons in this bond and these electrons in this bond. And that's the source of the repulsion. The electrons in the bond here are going to be close enough to repel each other. So this is the eclipsed conformation. It's higher in energy, and it's less stable. And so because of that, the repulsions between the electrons in the bond are going to encourage these to move to try to get farther apart. So I just rotated the back carbon about 60 degrees from the front carbon, and this gives us what's called a staggered configuration. And there it is, the dead-on end view. And when I draw these, I always try to keep the front carbon in exactly the same position, because it's mentally a lot easier the less things are changing and if I have a good reference point. So looking at, again, this molecule, trying to get it in the orientation I just drew, you've got the front carbon with the three hydrogens that are attached to it, 1, 2, 3, and if I have one of the hydrogens pointing straight up, you got a little triangle of things pointed towards you. Now if I look what's going on behind there, now you can see the other hydrogens are half between the hydrogens on the front carbon. So there's sort of a staggering there. You have one straight up, then one out off to the side and up, and then this one, and then the one straight down on the back carbon, and this guy. So this is the orientation. Again, the end-on view is what the Newman projection is representing, and you can see the three groups on the front carbon pointing towards you, the three groups on the back carbon pointing away from you. And for ethane, it's really easy to visualize simply an eclipsed conformation versus a staggered conformation. And these are sort of the extreme cases where things are spaced as far apart as they can get, or when things are as close as they can get. You have all kinds of odd angles, anything between 0 degrees when things are perfectly eclipsed. Like here, you can rotate the back one 1 degree or 2 degrees or 3 degrees, etc. When you get to 60 degrees, that's when you have a perfectly staggered configuration. This is going to be the lower energy conformation, which makes it more stable. So if you removed all the energy from the room, ethane would sit in its staggered configuration because that's more stable. So there we go. Basic Newman projections for the eclipsed and staggered conformations of ethane. And especially if you have access to your own model set, you can practice building these and then look at them from different perspectives and see how in this one the bonds get a little farther from each other. If you eclipse it, then the bonds get a little closer to each other, and that would be more repulsive. And so being able to see a model that truly shows the structure of the molecule is really beneficial. If you don't have that, here they are in the video, and you can find more pictures online.